why don't we get started? And so, of course, there is a homework due this evening. Please make sure that you don't wait to the last minute, and you should have already done the reading at this juncture. So where we left off last time, we talked about the sample median, and we had a demonstration in MATLAB as to why the median exists, and that is to represent the notional center or this idea of what is typical of values from some population, but it's a lot more robust than the sample mean. Yes, absolutely. Bless you, the sample mean is both unbiased, as we saw with our test for unbiasedness, and it is also consistent, as we saw with our test for consistency, which means it's a good replacement for the unknown ground truth parameter mu governing the population. But when you have these oddballs, these so-called outliers that you place among your measurements over which you compute the sample mean statistic, the sample mean can be moved very much if that outlier is very odd or extreme relative to what is typical. And so the median fixes that, or at least addresses that. And we had two examples of calculation of the sample median m hat. And this sample median, you use for the sample median two different procedures depending on whether the sample size n is even or odd. And so if it is odd, then we compute that or return that measurement that is exceeded by at most half the observations and at the same time and or preceded by at most half the observations. We saw also, then, if you have an even number of examples, in effect, you have what looks like two middles, right? And you take both of them and you calculate the average. And so in this case, we have the 4 and the 7 are the quote unquote two middles because we have an even number. You split it into two equal groups. And so we have the 4 and the 7 in this example, and we just calculate the sample median as being the midpoint between those two quote unquote middles. Okay. Any questions about this? That makes sense? Yeah. All right, so that's where we left off last time. Let's continue on going forward. So now we also have the so-called population median. If you have a ground truth population of values, you absolutely have a population median. And in the notation, the sample median is noted as big M hat. And we said our nomenclature or our standard was that anytime you see this hat over some variable, it's an estimator for the unhatted version of that variable. And therefore, m hat is going to be the estimator for m, where m hat is the sample median, was computed from a set of samples, and m is a so-called population median, right? The same way you can have a population mean mu, you also have a population median, big M. And so big M is related to the 0.5 probability associated with the governing the probability that governs a particular population of values that you are measuring. And so let's look at this population median, big M. And so it's the number whose value is exceeded with a probability not bigger than 0.5. And, bless you, it is preceded with a probability not bigger than 0.5. Now, in the slides that are on the blackboard, there's a typo. I corrected it here, and I'll push a new version up on the blackboard. So what does this mean? It means if you take the integral of all the values that are bigger than the population median M, that probability, the integral or the sum, put them all together, add them up, or take the integral if it's a continuous distribution, it's going to be no more than 0.5, right? And so because the population is trafficking or talking about a probability, we have to use the cumulative distribution function or something that looks like that. It's going to involve a sum or an integral. And so how you say exceeded, right, is by looking at the total probability. So there's a 50% chance that you're going to get a value that's bigger than the population median. If you are the middle value, all right, well, middle implies that half of all the possible values are going to be bigger than you. Okay. Likewise, that second point about the values preceded with probability not bigger than 0.5 for all the other values. That means that the second statement, probability that all the values the random variable can take on being less than m, the population median, is going to be at most zero point 0.5. So that means that there's a 50% probability that if you're going to get a value from a distribution, there's a 50% probability that it's going to be smaller than that population median. Um, Smaller than, 50%, less than or equal to 50%. And the reason why it says less than equal to is because sometimes you can't precisely split all the possible values into two groups. Okay? All right. So it might be 49 point something, 49.8 or something like that. Any questions about this? And so if you want to compute or calculate a population median, it requires you to sum or use integral depending on whether or not you have a discrete or continuous distribution. Okay. Any questions about this? All right. So there's a relationship between the population mean and the population median. And so population mean is mu, right? Population median is big M. We just got done talking about that. And that relationship will tell you something generally about the shape of the distribution. Now, of course, the reason why people care about the shape of a distribution is because that shape is going to tell you the values associated with this distribution that you would get, the values that you're more likely to see, right? And so if that curve for the distribution is higher up over a certain region of values, that means you're more likely to see those values given to you by the distribution if you were to sample. And so there are two or three rather different general descriptors about the shape of the distribution that you can tease out by looking at the relationship between the population median and the population mean. Okay, so the first one is symmetric or symmetry. If for your distribution, the population median, big M, is equal to the population mean mu, that means it's symmetric. So what does that mean? So, well, if you look at what is the most typical value or the middle value, and you go off some uh, difference in values to the left or to the right, that probability is going to be the same. It's reflected about the midpoint. And so let's say, you had some measurement of temperature, and that is a symmetric distribution. More specifically, temperature and most inertial quantities are governed by a normal distribution. It is a symmetric distribution. So if you're asking yourself what is the median temperature value for a particular day and time, and let's say you said it's 37 degrees Fahrenheit, right? So that means if you say 2 degrees more than 37, 39, or 2 degrees less than 37, 35, those two temperatures, 39 and 35, are going to have the same probability, right? So that's what symmetry means functionally. But if you were to plot the curve for the probability, you would get that this curve is the same if you reflect it about some midpoint or some point along the horizontal axis. Another way of testing for symmetry is you calculate the population mean, so the expected value of that random variable, and that gives you this mu, and then you perform that calculation for the population median, big M, and then you see if they're equal to one another. If they're equal, that probability is symmetric. Okay, so secondly, we have skewed right. Now, it's really easy to kind of mistake what skewed right means. And when you talk about skewness, what that refers to is the so-called tail of the distribution, right? And so the tail of the distribution is typically that longer part, and that longer part extends out in one direction. And so if you think about the tail of a distribution, if you were to integrate the tail of the distribution, sum up if it's a discrete distribution, or take the integral if it's a continuous distribution, there would be a very large percentage, the majority of the probability, the total probability, would exist in the tail of the distribution. So for example, if you took where this hump is here, the high point, that's called the mode of the distribution. It's the point corresponding to the highest or the biggest probability, the most likely value. If you were to integrate out going to the right here, you'd have a lot more of the total probability in going off to the right from this hump than you would going to the left. Likewise, when we have this picture here, skewed left, if you were to take the mode, so the value here associated with the biggest probability, if you were to integrate off to the left, you'd have much more probability resulting from that integral or sum than you would going to the right. And so when you talk about skewed, it implies that there's a preference for certain types of values, but skewness talks about in which direction the tail occurs for the distribution. So if you have a distribution that's so-called skewed right, what does that mean in terms of the relationship between the population median, big M, and the population mean mu? So if you have a distribution, you compute the mean and the median, both are population versions of them, and you find that the median big M is less than the population mean mu, that means it's skewed to the right, right? And if you look at the graph, you see that the tail extends off to the right. You're right. That means bigger values are associated with more probability for this particular distribution in total. Okay? All right. Any questions about this? That makes sense? And likewise, conversely, we could say if the population median, big M, is larger than the population mean mu, then we say that's skewed left. And if you look at the graph, you can see that the tail extends out to the left. Okay. And that's on page 214. And it's very easy to get this wrong because if you look at it, you say, well, the big hump is kind of mushed more to the left and mushed more to the right. And it's very easy to flip the two. A lot of people do that, including me sometimes. All right. Any questions about this? So why would someone care about skewness? Let's imagine that this graph represented, along the horizontal axis, a share price for some security, right? And maybe, you collected the share price for Apple stock or some other stock, Netflix stock, or what have you, over some period of time. If it's skewed in one direction, that means for this particular system, given the conditions over which you were measuring these share prices, that would mean that likely you would prefer certain types of prices. So if something were skewed, for example, right, this example, and you had a share price that was like right here, right, the highest probability share price, it's more likely at some point in time the share price is going to be larger, right, because you have more probability mass in that tail that extends out to the right. Okay. Does that make sense? And so people care very much about skewness of probabilities because skewness connotes an idea of preference of values. And when I say preference, I mean that there's a higher chance of getting certain types of values, larger values or smaller values. And for many types of probabilistic and statistical problems, you care if there is a preference by a system to give you larger values versus smaller values. Okay? All right, any questions about this? Make sense? Yeah. All right. So let's take a look at an example to solve for the population median big M. Now, of course, I just got done saying that you have to use the integral or the sum depending on whether or not your distribution is discrete or continuous. So let's use an example. We'll use a uniform distribution. It's fairly simple. It's easy to understand to jar your memory. So let me ask you, this is uniform, and the uniform is defined on the real number line between two points governing it, A and B, right? This is by convention. You could say B and A, but A is typically smaller than B in this particular notation that I try to mirror, on which I try to mirror the book. And so it's real valued. Let me ask you, is it continuous or discrete? Jar your memory from last semester. So it's real valued. It has to be what? 50% chance of getting the right answer. It's real valued. So if it's real valued, we're going to use integrals, right? So it has to be a continuous distribution because real values are uncountably infinite. Okay? All right. So it's continuous distribution, and therefore, when we solve for this population median, we're going to use integration. Okay? All right. So The probability density function, because continuous distributions have density functions, if it is a discrete distribution, that means the values over which you define the probability are either countable or countably infinite. Because those have mass functions, but continuous distributions, which are real valued measurements, have density functions. And so the probability density function for a so-called uniform distribution is as follows: 1 over b minus a for all values between a and b. And so if you were to plot the uniform distribution, you'd have probability of x, and x can take on values between minus infinity and positive infinity. And there are two values, a and b, defining your uniform distribution. And the distribution is 0 from minus infinity to a, the probability is, or the density function. And then once you get between a and b, you're going to have some non-zero probability. If you're greater than b, you're going to have 0 probability. So we have 0 here, and then this value is 1 over b minus a. And so that's exactly what the uniform distribution says, is that all of the real values in this interval, this closed interval on the real number line between a and b, have equal probability. Okay? All right. Any questions about this? Jar your memories? Okay. So given that, of course, we're going to need to integrate this in order to solve for what the population median is. Okay, so what is the cumulative distribution function? Well, the CDF is just the integral from minus infinity up to some value x. And what you're asking with the CDF is, what is the total probability represented up to and including a particular point? And so if I have x somewhere here, if x is here, well, it's going to be 0. If x is to the right of b, it's going to be 1. But if x is between a and b somewhere, it's asking what is this area that I'm shading here on the board, right? And that's what the CDF measures. And so how you note the CDF is just the density function. You integrate from minus infinity to x, substituting for that density function. Now, of course, this density function is defined so-called piecewise. Piecewise meaning that you define it by adding up what that integral is from minus infinity to x using all the pieces that you encounter along the way going from left to right on the real number line based on the definition of the values that you get for this density function. Okay? All right. So let's do that. And notationally, we write the CDF as capital F of x, whereas the PDF is lowercase f of x. Any questions? No questions? All right. So we'll set that up and we'll actually perform that integral, just substituting. So we have the integral from the bounds from minus infinity to x dx. And our f of x will substitute the density function for the uniform distribution, which is 1 over b minus a. Okay. So if we do that, we get the following piecewise definition. Well, if your x value is less than a, it's going to be 0, right? Because if you have the CDF between anywhere that's less than a, that value of the density function is going to return a 0. So if you integrate something that's 0, you're going to get 0. Okay. Well, if your value is x is greater than b, it's going to be 1, because in getting to some value greater than b, you're going to integrate everything area under the curve between a and b, which by law of total probability is 1, right? That's integrating all the values, adding up all the probabilities over which this thing is defined. So then in the middle portion here, this density function is going to be 1 over b minus a, which I just said. So if you compute the CDF, essentially what we're getting here is the following. Now you could actually do out the integral, or you could just reason from the appearance of the graph, you get the same result, right? But nonetheless, here it's x minus a over b minus a. And how you get that? Well, if you make an observation about the uniform distribution, well, you have a rectangle here. If you were to take the area under the curve between a and x, well, what is this width here? That width is x minus a, right? And the height here is 1 over b minus a, 1 over b minus a. So if you want the area of some, bless you, of some rectangle where the width is x minus a, and the height is 1 over b minus a, well, the area of a rectangle is just width times height. So you multiply the two together, and you get x minus a in the numerator, and you get b minus a in the denominator. Okay? All right, any questions about this? Okay, and this is in the book. And this is what your CDF looks like. So if we are to compute this population median, we need the CDF in order to do that, because that's exactly what this P of x less than big M is at most 0.5 is exactly this P of x less than M is exactly the CDF. Okay? All right, where you're substituting big M for x in the expression for the CDF. Okay. All right, so let's take a look at this, and we're just going to set this expression equal to 0.5, right? And then we're going to use the CDF to solve for what M should be. So this means the CDF evaluated at big M is equal to 0.5. So if we substitute this definition, this piecewise definition for the CDF, this big F that we just derived, we'll see what we get. So that means that our x value, right, is going to be substituted for the parameter for the CDF is going to be big M. And so everywhere we see an x, we substitute big M. So we're going to substitute a big M here in this expression. And recall, we set this equal to 0.5. So we have in the numerator big M minus a, and in the denominator we have our b minus a. That's set equal to 0.5. Okay. Everyone understand this step? Any questions about this? So this is substitution based on the definition for the CDF of the uniform distribution. Okay, so if we do that, we do a little bit of algebra. We multiply both sides of the expression by b minus a, and then we divide both sides of the expression by 0.5, and we add an a to bring the a to isolate big M, and we end up with big M is equal to a plus b over 2. Right? And if you think about it, well, if A is the low bound where the uniform distribution is defined, and B is the high bound where the uniform distribution is defined, well, A plus B over M is A plus B over 2 rather is right here in the middle, which is exactly the middle value associated with this probability, right? So if we, just to kind of verify this, we wanted to look at the area under the curve here, well, if we have big M, that point here is A plus B over 2. That's M. If we were to take the area under the curve for the right-hand region, and the area under the curve for the left-hand region, each one would be equal size, representing half of the total probability, or 0.5. Right? So we could just kind of do this as like a b minus a plus b over 2, and then multiply by b minus 1 over b minus a, and then we'd have an m minus an a plus b over 2 minus a, and then we'd multiply that by 1 over b minus a, and you could actually equate the two and show that they are equal. Okay? Any questions about this? Does that make sense? So the population median is something that you absolutely have to calculate. Now, of course, we talked about this idea of skewness, and maybe you wanted to ask the question, is what is the general shape in terms of skewness of the uniform distribution? Well, you can see from the uniform distribution that it's symmetric, but mathematically, we can also prove this, because you can't always rely on what you see from the graph, okay? So if we take our uniform distribution and you actually compute the expected value, you'd find the expected value, the population mean mu, is equal to 1/2 times quantity A plus B, which is exactly what the population median big M is, right? And so the two are equal, and because they're equal, that means the uniform distribution is symmetric, okay? And you can do this with every single distribution that we've studied. You can do it with the Bernoulli, the binomial. You can do it with the Poisson, the gamma, the exponential, and the normal distribution. Okay? All right, any questions about this? Does that make sense? And so skewness is a measure, a gross level measure, a coarse measure of the shape of a distribution, and you care about skewness because you care about the preference, if you will, in terms of the values that you're going to get from this distribution. Does it prefer big values and small values equally? Does it prefer big values more than small values, or vice versa? Does it prefer small values versus big values? Okay. All right. Any questions? No questions? That makes sense? No? All right. So, um, let's compute the sample median in an example. And for this, and this is on page 217 in the book, and we're going to take that same set of measurements representing the CPU time of 30 processes sampled from the system. And so each row has 10, and we have 3 rows of 10 for a total of 30 such measurements. And so you gather your observations in computing your sample median. This is big M hat, and then you sort them in some order. It could be non-decreasing order. Typically it's non-decreasing, but you could do some other ordering, but you have to make sure you're adhering to and sticking with the convention. And so if the value is odd, then you're going to take n plus 1, where n is the number of observations you have, and divide by 2, and the n plus 1 over 2 smallest observation is going to be your sample median, right? So that's mathematically how you calculate it. You get n inputs, you add 1 to it, divide by 2, and in your sorted order, you iterate to that particular position in your sorted order, and that's your sample median if the input has an odd size. If the input is even, then given the number of measurements you have, you're going to take n, the number of examples, another number of measurements you're given, divide by 2, and then you're going to take that n and you're going to add 2 to it and divide by 2. And so these are the two middles that I alluded to a few slides ago. And then you're going to take the two middles, that at the n plus second n over 2th position and the n plus 2 over 2th position, if that's the right way to say it. And you're going to take the midpoint between those two. So in this example, we have 3 rows of 10 for a total of 30 measurements, right? 30 is an even number, so we're going to take the approach prescribed by step 3 on the slide. And so, okay, well, 30 over 2 is 15, right? Okay, so that's going to be one of our middles. It's the 15th position in sorted order. And n plus 2 over 2, so that's 30 plus 2 divided by 2 is 16, right? So we're going to look for the two measurements in the 15th position and the 16th position and calculate the midpoint. Okay, so if it's 10 in each row, so that's 10, another 5 is 15, so number 42 is the value for the 15th position. The position just to its right, its successor, is 43. That's in the 16th position. And so we take 42 and 43 as our quote-unquote two middles, and we take the midpoint between the two. That's 42.5. And our result for this example is our sample median big M hat is 42.5. Okay. Now you could all do this in MATLAB quite readily. There are some existing APIs built in, but oftentimes, it's a good exercise to reinforce something when you implement it yourself. Okay. Any questions about this? Make sense? Yeah? Okay. So these are just some terms here, and it's important in any discipline to understand the lingo. And I'm not going to belabor these, but it's really important to familiarize yourself because you see these things pop up all the time, both in our textbook, but as well as in the literature if you go off and look stuff up. Okay, so mu is a population mean, x bar is the sample mean. X bar is the estimator for the population mean. Sigma is the population standard deviation. S is the sample standard deviation. We haven't talked about that yet. S is an estimator for sigma. S squared is the sample variance. Sigma squared is the population variance. S squared is an estimator, and I'll just kind of wave my hand for that because it's not correct, completely correct, and we'll talk about that. But at this juncture, we'll say that S squared is an estimator for sigma squared. And then lastly, we just talked about the sample median M hat, and M hat is an estimator for the population median big M. Okay, so please familiarize yourself with the notation. All right, So let's take a look at dispersion. Now, last semester in stochastic, we talked about variance and we talked about standard deviation as measures of dispersion, but there are other measures of dispersion that have better robustness qualities. And let's talk about that. So the median, if you think about what it does, the median generally splits a distribution into two equal parts as far as the population of values that you could observe, right? And so sometimes it's important to look at more than just the halves of the distribution. Sometimes you want to look at those values that effectively split the distribution into parts. Like maybe you're interested in 4 parts of the distribution, or maybe 10 parts, or any other arbitrary type of percentage of this distribution. And the reason why you care about, or should care about, splitting up a distribution into equally sized parts, and when I say equally sized parts, I mean the amount of probability represented by each piece of the distribution. The reason why you want to split it up into parts, because sometimes you want to observe how that probability changes or is distributed or is kind of spread out around different regions of values. And so you might want to know, all right, if I have relatively small values within some tiny sliver of values, how much preference does this system have in giving me these measurements, right? So it really is valuable to know how your distribution behaves, as it were, for these very fine-grained slivers or ranges of values that this system can give you if you were to sample from it. And so you might want 4 parts, you might want 10 parts, or some arbitrary number of parts. And in this diagram here, on the horizontal axis, I have marked here Q1, Q2, and Q3, and each one of these collectively represents a so-called quartile. And they're called quartiles because if you were to take the area under the curve for this probability distribution, it would represent 0.25 probability, or 25% of the total probability, right? And so splitting up into 4 parts, you call them quartiles, but we also need a system to talk about an arbitrary percentage as far as these parts of a distribution is concerned. So there's something called a p-quantile. A p-quantile kind of looks like the population median, but instead of talking about 0.5, you're talking about arbitrary fractions, point something, right? And so a p-quantile is that value little x such that no more than no more than p probability mass, a proportion p, is in that region of the distribution. So just like the population median, we're going to integrate if it's a continuous distribution, or sum if it's a discrete distribution, and we're looking for that proportion of values that are less than this particular quantity of interest, right? That's called a quantile. There's something called the sample version of the p-quantile, right? And so we saw the sample median, right? The sample median is a sample 0.5 quantile, right? Whereas the population median is a 0.5 quantile, right? So there's a 0.5 quantile and the sample 0.5 quantile. Those are the population median, big M, the 0.5 quantile, and the sample median, big M hat, which is the sample 0.5 p quantile. And so the latter, the sample p quantile, it's a number, so it's a value that exceeds at most 100 times p percent. So the sample median, it exceeds 50%, right? So if we said p is 0.5, 100 times 0.5 is going to be 50, and that's expressed as a percentage. And so the sample p quantile is a number exceeding at most 100 times p, our proportion, is a percent of the sample. And it is preceded by 1 minus p as a percentage, so you multiply by 100 of the sample. Okay? All right. Any questions about this? Does that make sense? So there's also a gamma percentile, right? Now, when, maybe whether it's, you know, uh, GREs or something like that, someone takes a standardized test and you get back your result and it says, hey, congratulations, you're in the 90th percentile, right? That is a percentile, and that gamma is going to be that number when they say 90th percentile. That number gamma is 90 in that example. And so what that represents is the percentage of the population that is less than you, right? If you were to rank them all together. And so this gamma is multiplied by zero point zero 0.01 when you want to express it as a quantile. So if you said someone got 90th percentile, gamma is 90. So you take that 90, you multiply it by zero point zero 0.01, that becomes zero point 0.9. And so you say, I'm in the zero point 0.9 quantile. Or you could say I'm 90th percentile. Does that make sense? So this is just notation, but it is convention, and it's really important to understand the differences so that when you go off and you read things, let's say, in a project you're doing some research and you go off and read things to understand the well-accepted terminology from statistics. Okay. Any questions about this? That makes sense? Yeah? All right. So let's generalize this idea, the median, right? If we were to look at the quantiles, the quartiles rather, the quartiles split your distribution to 4 equal parts. There's something called the first quartile. That is the first part here, Q1. So Q1 is the first quartile, or the value that splits your distribution into among with the others into 4 equal parts. And so the first quartile is the 25th percentile, right? Because it splits off 25% of the values are less than the first quartile. The second quartile you could call the 50th percentile, right? That's the median, right? Because it's the middle percentile, right? It splits everything into half and half, 50% of the probability. And then the so-called third quartile, right? That's exceeds all values, 75% of all values. So that means that cumulative distribution function is less than equal to 0.75. And so the third quartile is also, you could equivalently call it the 75th percentile. Does that make sense? And so this is just notation. You could call the median the 0.5 quantile. You could call the median the 50th percentile. You could also call the median the second quartile, right? You can sort of interchangeably talk about the same quantity or the same idea using different notation. And so it's important to understand this because for all varieties of reasons, people might describe the same thing differently. So it's important to understand the vocabulary and the notation. Okay, so this is some other notation, and this is using symbols. And I'm not going to belabor this, but again, it's still important to understand the notation. This is a scan from the textbook. Okay. So, spread or dispersion. Last semester, we certainly talked in stochastic about standard deviation, and we talked about variance. And so if we were to look at these two graphs here, we have some measure of interest. It doesn't matter what the measure is. I just pulled this graph from online somewhere. We have the pink curve and we have the blue curve. And you can see just by eyeballing it that the blue curve is more narrow. And what does that mean? It means that the probabilities, the projection along the vertical axis, are defined on values that range from about, let's see, about 10 up through like 37, right? For the pink curve, we have a wider range of values, something less than 0, up through like 43, 44, right? And so for certain systems, it's important to understand not necessarily the amount of probability, but the broadness of the range of values that you could see. Take, for example, when you're trading securities, you're buying and selling shares of stock. In finance, the word for dispersion of the distribution of values is called volatility, right, or risk, if you will. And now, the reason why you care about the spread of a distribution as it pertains to buying and selling securities is because if the spread is wider, that means the share price could jump up or jump down more vigorously. And of course, if you're not careful, you might end up buying something when it has already jumped up, and then it's going to go on its way down shortly thereafter if you have a time horizon over which you have to trade that security, right? So people care very much about dispersion of a distribution for other reasons. Let's say, you're designing a mechanism, and that mechanism is vibrating, and you have a sensor that's going to measure the amount of vibration on that mechanism. And if your dispersion is wider, representing the distribution for the vibration for that mechanism, well, mechanisms that function well shouldn't vibrate too much, because vibration, you could end up shaking something loose. If it's something that transports people, it's not going to be comfortable, or it could be quite dangerous, and you could have a catastrophic failure. So people, for a variety of reasons, are very, very concerned about measures of spread or dispersion. Okay, and so given a sample, right? X1, X2, X3 up through and including X sub n. It doesn't matter what the quantity under measurement is, but you have n, big N, I'm sorry, little n, many samples. And so the sample variance, S squared, is as follows. And this is not a typo. S squared is 1 over n minus 1. So you have n many samples. So if you had 100 samples, 1 over n minus 1 would be 1 over 99, right? And so we have the sum for I goes from 1 to n of each measurement x sub I minus the sample mean x bar, quantity squared. So x bar, sample mean, we already talked about that. So you're going to compute, the sample mean, and you're going to subtract that from each one of your measured values, and you're going to square those differences and multiply by 1 over n. Now, there's a reason why it's 1 over n minus 1 as this leading scalar. I'm not going to tell you that reason, because that's going to be on an assignment for you to figure out why that reason is. But at this juncture, just accept that this is true, because it is true, right? There are other versions of the sample variance, but this is the one you really want to use. Okay, so this is the variability or dispersion between the examples and the sample mean. And if you look at that term, that squared term in the parenthesized expression in this definition for sample mean S squared, it's subtracting off, so it's taking all the differences between each measurement and the mean, and the squaring means that you don't care about the direction. You don't care if the measurement X is bigger than X bar or if it's smaller than X bar. What you care about is the magnitude, okay? And so S squared is an estimator for population variance. So that means that if you don't know what sigma squared is, right, you can calculate S squared. And absolutely, you could do a simulation like I did with the sample mean X bar and show all sorts of things about it. Okay? All right. Any questions about this? Does that make sense? Yeah. All right. So what is the sample standard deviation then? Well, we're going to take the square root of S squared. So the sample standard deviation, little s, is equal to the square root of S squared. Now, the same reason why we had the population standard deviation, sigma, is the same reason why we have little s. S squared, because of that squared term, right, your unit of measurement is squared. So if you're measuring temperature, that would be, say, for example, degrees Fahrenheit squared. And when you say degrees Fahrenheit squared, it's really hard to compare that to the central value. So for example, if you say, how much will my temperature today vary, right? This morning it was 26 degrees. Now, if you listen to the news report and they said the average temperature is going to be, and I'm just going to make this up because I know it's going to hit 46 today. If the average temperature were like, for example, 40, right? No, like 30, 38 degrees, right? And you said, oh, the average is 38 degrees. By how much is this thing going to vary, the temperatures today? Now, if they said it's going to be plus or minus 36 degrees squared, what does that mean, right? Because it doesn't allow you to make comparisons between the average relative to the average if someone says degrees squared. And so if you take the square root of that, I could say it's going to be 36 plus or minus 8 degrees Fahrenheit. So now I can say plus or minus 8 degrees Fahrenheit, and that gives you an idea of relative to the what is typical, the midpoint, how bad can it get or how good can it get, right? And so for the same reason that we took the square root of sigma squared to get the standard deviation, we also take the square root of S squared to get the sample standard deviation, okay? Right, any questions about this? Does that make sense? Okay, so let me do a time check. I thought I'd have more questions, so I kind of budgeted for questions. All right, so this S is an estimator for sigma, and you can use this S to stand in place for the population standard deviation. And so you're expressing, when you talk about S, you're expressing dispersion in the same units as M, and you're also expressing dispersion in the same units as sigma. You want to have the units for the midpoint the same as the units for the representation of dispersion, because that gives everyone an intuitive sense of what it means relative to what is typical. Okay? All right. Any questions about this? No? All right. So, there's something called standard error. Any estimator has what's called a standard error, and the standard error is that name given to the standard deviation of that estimator, right? So when we had X bar in that MATLAB example, we set a sample size and we calculate that sample from a population of ages, and then we measured X bar, the sample mean. And then we did that some number of times over some number of trials, 200 of them, I believe. And then we could show what the variability is for that measurement, right? When you look at the standard deviation for that measurement, we give it a different name, and that's called the standard error. Okay. All right. So given any estimator or statistic, theta hat, its standard deviation is called its standard error, right? And so you say the standard error of estimator theta hat, or, and this is some notation that you'll see, sigma of theta hat, right? So we'd say sigma of x bar refers to the standard error of x bar, where x bar is the sample mean measurement. And I'll show this in MATLAB in a second or two. And so we say that's the standard error of our estimator. And so going back to our example of MATLAB, let me fire up MATLAB in the time that we have left. Let's see, it is now 10:20. So we're out at 10:45, right? So let me see if I can do this in 25 minutes. So let me pop out of here, and provided our license server is still going, yes it is, let me run MATLAB, and I will take that example we had from before. Um, that was sample mean outlier. I don't want that one. Uh, Analytics MATLAB. So let me go up one and make sure I can add, I have MATLAB on my path so that I can actually, folders and subfolders, um, test sample mean um, variance. There we go. So let me do this one. Let me use this one. Okay. So I'm going to save this uh, to a different name, and I'll certainly after probably this evening or so, I'll post the result of what I'm doing today. So test sample means standard error. Oops, standard error. Okay. So I have my example. I have a bunch of population members based on their age. I measure the ground truth population mean. Okay. Um, I look at the um, sample size is 10. Let me set the sample size back to 10. The number of trials is 200, so 200 many times. I'm going to take a sample of 10 people from the population, and then from that sample, I'm going to compute the sample mean, and then I'm going to show how that variability changes when we change the sample size. Okay. So here I measure sample mean here. So I measure it 200 times in that loop for t with num trials. I have the population mean, that's for plotting purposes. And so I also here at the bottom, um, I computed the variance, right, of the sample means. Okay, so I have the variance of the sample means, and I can compute the standard error of the sample means by just taking the square root of the variance, or I could just say standard error of x bar is equal to standard error. Oh, see, make sure that's standard error. I'm sure it is. Standard deviation. Okay. Standard deviation of the sample means. Okay. So again, this isn't very interesting. What would make it a lot more interesting is if I did this experiment more than once and then plot them along a graph, but I'll probably, in the interest of time, save that for our next class since we only have about 15, 20 minutes. Um, so for now, I'll just plot the standard deviation. We saw that the variance changes, and if the variance changes, so too does the standard deviation. So let me clear that, CLC, and then I plotted the variance of x bar, right? So let me have another message I display. Message equals s printf uh, standard error x bar is equal to percent %f backslash n standard error x bar. All right, so let me save that, and I'll just display that message, and let me save it. Let me run that. And as you can see, the standard error for a sample size of 10 is 9.4 and change. So if you said by how bad can this get? Well, you just take the sample mean and say plus or minus the standard error. Okay, and that gives you the same units as the midpoint, which is the mean. And so let me go ahead and I'll change the sample size to be something in order of magnitude larger. So instead of a sample size of 10, I have a sample size of 100, and we'll see how that impacts the standard error. I mean, absolutely it does. And so now it's plus or minus 2. And actually, it's maybe a blessing in disguise that I did not get rid of the first graph. And you can see here um, the red graph going straight across in the middle, that was the population mean. The blue was what happened to the variability. You can see it swings really broadly when we had a sample size of 10. And then this kind of, it looks gold or yellow. You can see it's a lot less jagged, swings less up and down. That's the version of X bar over my 200 trials as a result of having a sample size of 100, right? And that plays out with standard error here. You see plus or minus 2.8. If we were to take the actual value and blow this graph up really, really big, you'd see it swings at that value of like 50, I think it was 55 and change, plus or minus 3 for the golden yellow colored graph, plus or minus 2.8. Okay, does that make sense? Any questions about this? Okay, so again, it's a lot more interesting, and I'll do that on Tuesday if we run this 200 trials more than one time and actually show you the relationship between the standard error and the ground truth population mean. Okay, all right. Any questions? Does that make sense? Yeah. All right, so let me get rid of this and let me pop back into the slide deck and let's continue on. All right, so we can use the standard error to depict how reliable an estimator is, right? And so when we talk about reliable, we mean how does it behave over time? And so here we have a bunch of different graphs, and we're going to show how standard error and biasness can be used to describe the behavior of an estimator. And then we're going to show the relationship of that estimator, theta hat, to the ground truth parameter. And so you can imagine in the MATLAB example that we had carried forward, we had the ground truth population mean mu. Now, I showed it to you and we did it in MATLAB, but in reality, for things like the homeless population or any kind of real problem, you don't have access to this ground truth population mean mu. What you do have access to is samples. And so we said that if you compute the sample mean, and the sample mean, if you have your sample size big enough, that it becomes a really good replacement. But if you did that multiple times, you want to know how reliable is this sample mean given the conditions under which you're operating in the system that you are instrumenting and trying to reason about. And so here in this first graph here in the upper left hand corner, there are 4 of them, we have our ground truth population parameter mu, right, or theta, right? And theta has a value. And you saw that value in the homeless population and in the age simulation, it does not change, right? And so we have our fixed population parameter theta, and that can be some value. It's hidden from you. Now, every time we took a sample of size 10 or size 100, we got a value for theta hat. That was our sample mean X bar. Now, of course, X bar changed over those 200 many trials, right? And so what we're looking at here is given the set of different values you get for sample mean X bar or your estimator theta hat from one trial to the next trial to the next trial, how do these values clump together relative to the ground truth? Because if you want to use theta hat as a replacement for theta, you want to know, how does theta hat change? Does it change? Does it change a little? Does it change a lot? So in this graph here, the first one on the upper left-hand plot, it's a biased estimator with a high standard error. So remember when we showed our proof and we said that X bar is unbiased, right? So I'm showing you here what the consequence is of having these tests come back as false in different ways, right? So here in this upper left-hand corner, we have a biased estimator theta hat, and it has a high standard error. Biased means that there's a preference for certain types of values. In this case, you'll notice here, each of these dots represents a value that's given back by theta hat, so the result of computing a statistic. And so what it means here, if you look at this, you see that there's some dots here that are smaller than theta, our ground truth, yet unknown population parameter, but more of the dots are bigger than most of the dots are bigger than our ground truth population parameter theta. And so the fact that there's a preference for larger values, that implies that there's a bias. That's what biased means. There's a preference for certain types of values. Okay. You'll also notice not only does it prefer larger values for our theta hat, these values are also really spread out, right? So we have some values that are relatively, only mildly larger than theta. We have some that are a lot larger than theta. They're spread out or very dispersed. So that means this value is going to jump around, and that's exactly what we saw when we only had a sample size of 10. You saw that the value of X bar, it kind of swung really, really high, really, really low. It was very choppy, very jagged. Okay. So if we cast our attention here to the right, your right, this upper right-hand graph, this represents an unbiased estimator with a high standard error. So when we had that test, is your estimator theta hat unbiased, right? What unbiased means is there's no preference for any one type of value. And what you'll notice here, again, we have our ground truth theta, the hidden population parameter in the center, and then each one of these dots represents a different instantiation of theta hat, right? So we ran this test, this statistic, 200 many times, defined by the trial number, and you notice here it's spread out, right? There's like an equal number that are, medium size, large size, small size, negative large, negative medium, and so forth. So that's what unbiased means. It's fair, right? It prefers all outcomes for the result of this theta hat, this statistic. Everything's equally likely. It doesn't have a preference per se for one type of value or another. Now, high standard error, well, it's very dispersed. The values can swing from a really large negative to a really large positive. So again, while it's unbiased, it's fair, but it still swings very broadly across a bunch of different values they can take on. Okay, so let's now look at the bottom left-hand graph. This is a biased estimator with a low standard error. So our theta hat, it's biased, so it prefers values that are larger than our ground truth population parameter. So you see all these instantiations, these dots representing different outcomes of calculating our statistic theta hat. You notice they're all in this region greater than our theta, right? So there's a preference for certain types of values. But in that preference, it's very closely clumped together. It's not going to vary very widely. And then lastly, this is the ultimate that you really want with any sort of estimator. We have our ground truth parameter, theta, and we have no preference really for any particular value, right? All these values are roughly equally represented that our theta hat can take on, represented by each one of these dots. And moreover, the range over which this thing takes on values is relatively small, okay? And so we talked about this idea of this test for is it unbiased, is it consistent? Now, when you want to know if a statistic is a good replacement, an estimator, is it a good replacement for a ground truth population parameter? Sometimes this test will say, nope, it's not unbiased, it's biased. And that's not catastrophic because if you know the way in which it's biased, now you can make adjustments in your interpretation or in your methodology, right? And so simply by knowing the behavior of your estimator will help give you tools, if you will, to make better informed judgments. And so ultimately, do you want a statistic that's unbiased with low standard error? Absolutely. But there's a trade-off. Maybe to get low standard error, you need a sample size for which you can't afford the MIPS, right? What do you do then? Well, either you tether your system, meaning that give your system some communication ability, and then you send some information off to a data center where you can do a lot more computation, right? Or you have to relax what it is you're trying to do, right? Deal with the fact that you have some variability. But simply knowing if there are preferences in place and what the variability is, you can better make use of what your estimator is telling you. Because at the end of the day, if you're going to commit resources or make policy decisions and do all sorts of things as a result of your statistic, um, understanding the behavior of your statistic, you could either go with it and make adjustments, or perhaps you do some transformation to try to change the behavior of your statistic. Okay? Any questions about this? Does that make sense? And so this is in the book, and in MATLAB on Tuesday, I will do some simulation based on this age simulation that we've been carrying forward to show you an equivalent of this graph in MATLAB. Okay? All right. Any questions about this? Does that make sense? Okay. So other ways to measure dispersion. So sample mean, variance, standard deviation, they're all sensitive to outliers. That's if you have an extreme observation, it can perturb or move this value, right? And so there's another way of measuring dispersion called the interquartile range, and that is not as sensitive to outliers. Let me check the time here. 10:36. Okay, and so we have our quartiles, and a quartile is a quantile that separates or partitions your distribution into 4 equal parts as measured by the area under the curve. And so we have the 0th quartile you could consider as being the starting point here, but we really only talk about the 1st, 2nd, and 3rd quartile. And so the so-called interquartile range, or IQR, is just the numerical difference between the value represented at the 3rd quartile and the value represented at the 1st quartile. This so-called interquartile range, you see it all the time in all sorts of reports. And you can look at these values as a measure of dispersion. And if you think about it, well, if this distribution is very wide, what's going to happen is if it's very wide, that means Q3, it's going to be all spread out. And if it's all spread out, that means Q3 and Q1 are going to be further apart from one another. If this distribution is very narrow, well, that means they're all clumped together, and that means Q3 and Q1 are going to be relatively close to one another. And so for that reason, the interquartile range is a really good measurement of dispersion. Okay, and so the sample interquartile range, or IQR hat, is just Q3 hat, the 3rd sample quartile, minus Q1 hat, the 1st sample quartile. Okay, and so it just so happens that 99.3% of the population of values fall plus or minus 1.5 IQRs, 1.5 IQRs from the quartiles. And I explain what I mean by this. So you take Q3 and you take Q1 and you subtract and you multiply that by 1.5. And now you can use that 1.5 in something that looks almost like a standard deviation. You can say the midpoint plus or minus something, but instead of the midpoint, it's distance from Q1 and distance from Q3. Okay, so let's take a look at this. Here we have some values, right? And these values, I have 12 of them. and their values are literally numerically 1, 2, 3, 4, 5, 6, 7, 8, 9, up through 12. And so we said the quartile is a number exceeding at most 100 times p% of the values, where p is 0.25. And so what makes it a quartile? P is 0.025 for the first quartile and 0.75 rather, 0.25 for the first quartile and 0.75 for the third quartile, representing the 25% point and the 75% point. Okay, so let's take a look at this. 4 is the first quartile that exceeds at most 25%. And so here we have 12. 25% of 12 is 3. So this value 4 exceeds at most 3 of these values in non-decreasing order, right? Likewise, 50% or half of 12 is 6. So this 0.7 exceeds at most 50% of our values, right? That's the second quartile. Now, 75% of 12 is 12 divided by 4, 3, 6, 9 is 9. And so this value 10 exceeds at most 75% of the values for this example. And so there I've identified my quartiles. Q1 is 4, Q2 is value 7, and Q3 is value 10. Okay. Any questions about this? Does that make sense? Okay. So let's go forward and let's compute our interquartile range. So interquartile range is the numerical difference between the third quartile, which is 10 in this case, and the first quartile, which is 4 in this case. 10 minus 4 is 6, right? There's also an example in the book similar to this. So the interquartile range is 6, and 1.5 IQR, if IQR hat is 6, 1.5 times 6 is 9, right? So that gives us 1.5 times the interquartile range, the sample interquartile range. So I take that 9 and I say, okay, well, let me subtract 1.5 IQR from the first quartile. That's minus 5. So the first quartile is 4, minus the 9, which is 1.5 IQR, right? That's minus 5. And so let me add that 1.5 IQR to the third quartile. So the third quartile is 10. Adding 9 to that is 19. So now that gives me an interval. That gives me an interval on the closed interval on the value or whatever set of values these are drawn for. If it's integers, I'll say integers. If it's reals, I'll say reals. And we have a closed interval from minus 5 on the low side up through 19 on the high side. So that means for whatever system I measured these numbers for, I have a 99.3% probability that whenever I sample subsequent values, those 99.3% of the time, that between this range of minus 5 and 19, I'm going to get a value from the system. So what does that mean? Well, that's a measure of dispersion because 99.3% of the values are in this range, and I can actually look at how wide that range is. And so this interquartile range, for some values that I measure from some distributions, I'll see that this value is more narrow, this interval. For other distributions, I'll see that this value is more wide. And so IQR works just like variance and standard deviation, only it uses the quartiles instead of a calculation that is more susceptible to outliers, more brittle to outliers. And so standard deviation is not robust, whereas interquartile range is a lot more robust to oddball or outlier values. Okay. Any questions about this? Does that make sense? No questions? All right. So that's all I had. So we will pick back up on Tuesday, and I will go through that example about biasness and standard error as it relates to sample statistic to round out the example that we had using the sample mean with our simulation of ages of members of a population. Okay, so we have the homework due tonight. I look forward to your submissions, and I will see you all on Tuesday.